Welcome to the Organic Chemistry video content to accompany the Organic Chemistry 1 lecture guide and the Organic Chemistry 1 primer. The problems in this part are from Part 1 concerning structure, stability, and conventions. Our first problem deals with converting condensed formulae to Lewis structures. In our first problem, we have this atom in parentheses. When you have a unit in parentheses like that without a subscript, it indicates that that unit is coming off of a growing chain represented by the rest of the condensed formula. So if we start out drawing this formula as a Lewis structure, we have a CH3 unit at the end, then we have a carbon. Coming off of that growing chain is the oxygen atom that's in parentheses. Then we continue the chain with this OH unit. Once we have that basis of the structure in place, we can check to see whether each of the atoms in our formula has the correct number of bonds. In order to do that, we have to draw the Lewis symbol for each of the atoms. Hydrogen is in group 1 and can make 1 bond. Carbon is in group 4 and has 4 unpaired electrons in its valence shell, drawn here in the Lewis symbol. It can make 4 bonds. Oxygen has 2 pairs of electrons, which should be pairs in our structure, so we'll fill those in. And then you see that there are 2 unpaired electrons in the valence shell in the Lewis symbol of oxygen. Oxygen in neutral compounds will generally, that means, make 2 bonds. If we look at our structure, this oxygen has 2 bonds, and this carbon has 4 bonds, and each of the hydrogens has 1 bond. But we have a carbon here that only has 3 bonds, and an oxygen here that only has 1 bond. By adding a bond between the two, you're able to accommodate the correct valence, the correct number of bonds for each of those 2 atoms. And now we have the correct structure. Our next example illustrates another way that parentheses can be used in condensed formula, and how we have to convert those to the Lewis structures. If we have a parentheses with a subscript, that indicates that the unit in the parentheses is repeated 2 times in this case, whatever the subscript is. Whereas if we have a unit in parentheses without a subscript, it's going to be a unit coming off of the chain, just like the oxygen in our previous example. So now we can start out drawing our CH3 unit at the end, and now we have a CH2 in parentheses listed 2 times. So we need 2 CH2 units to continue the chain. Our next unit is a CH unit, CH. And then coming off of the chain is our CH3 unit in parentheses. So we have a CH3 coming down off of the main growing chain, like that. We then continue our growing chain with a CH2 and a CH3. And now if we count up the bonds in our structure, each of the carbons has 4 bonds, each of the hydrogens has 1 bond. So this is the correct Lewis structure from this condensed formula. Our next problem down here has hydrogen, carbon, chlorine, and oxygen. Now, up at the top of the page here, we've already drawn the Lewis symbols for hydrogen, carbon, and oxygen. If you look at the periodic table and draw the Lewis symbol for chlorine, chlorine's in group 7, so you should have 1 unpaired electron in that Lewis symbol. You will generally, in neutral compounds of chlorine, have 1 bond to chlorine. Armed with that knowledge, we can now draw our Lewis symbol, starting with a CH3 unit at the end. Then we have a CH unit. Coming off of that chain is a Cl. Then we continue the chain with a carbon. Coming off of the chain is an oxygen. And then we have a hydrogen as we continue the chain. We know that oxygen should have 2 lone pairs. Chlorine should have 3 lone pairs in this neutral compound. And we find that the only atoms that don't have the correct number of bonds in this Lewis structure yet are the carbon and oxygen, each of which needs 1 more bond, and we accomplish that by making a double bond between the 2. And now we have the correct Lewis structure for that condensed formula. You may come across condensed formulae like this one in the last problem on this page, where instead of having the chain drawn out explicitly, they will just list the number of carbons and hydrogens, perhaps followed by some unit that comes at the end of the carbon-hydrogen chain. When you're doing a condensed formula like this, it's best to draw the chain of carbon and hydrogen atoms which are very common types of chains in organic chemistry. And then draw the next unit, the OH in this case, at the end. So we've used our 2 carbons and our 5 hydrogens making this first part of the chain. With the O and its 2 lone pairs and the H, we now have the correct Lewis structure given this formula as well. Organic chemists use the Linebond notation as a way to draw organic molecules in a more condensed fashion by leaving off any hydrogen atoms that are on carbons. So if you're converting these Lewis structures into Linebond structures, the carbon chain would be drawn simply with 2 lines like this. Any junction or bend in the line or change in bonding in the line or the end of a line represents a carbon atom. So this is 1, 2, 3 carbon atoms. You don't have to draw any hydrogen atoms that are on carbons. You do, however, have to draw any atoms that are not carbon. And you can show the lone pairs or not. You'll see them drawn both ways depending on what purpose one has in drawing the structure. If we move down to this example at the bottom, you can draw out the 4 carbon atoms just by drawing that shape using just lines and not having to draw the C symbols. Drawing in the symbols for any atoms that are not carbon and that are not hydrogens attached to carbon. So this would be the correct Linebond notation for that structure. If we have a more complicated structure like over on the right hand side, we can see just how much simpler it will be to draw a structure with a Linebond notation than in this Lewis formation. If I have 2 carbons triply bound to each other, again I don't have to draw the carbon symbols here. I just draw 3 bonds, and then I have a single bond going to this carbon atom, and that's right here, going up to this carbon atom, which has a methyl group up at the top, which I've just drawn there, and then this goes down to this nitrogen. You must draw hydrogen atoms if they're on non-carbon atoms, so I'll fill that hydrogen in. That nitrogen moves up to a carbon. I'll have that bond there, and I have 1, 2, 3 CH3 units coming off of that. 1, 2, 3. And I don't have to draw those H's in, so you see it's much more condensed and a much quicker to draw structure in the Linebond notation than drawing out the whole Lewis structure where you have all these hydrogen atoms as well. Now you might sometimes find it useful to know where all the hydrogen atoms are in a structure, and to convert Linebond structures to Lewis structures, you'll have to know that a carbon atom, particularly, has 4 bonds when it's neutral. In all these cases, we have neutral atoms all around. So any end or bend in a bond is a carbon atom, and the hydrogen atoms are implied but not explicitly shown. So when you're converting to a Lewis structure, you have to say, well, this carbon needs 3 additional bonds to get to the traditional 4 bonds that carbon has in a neutral compound. The carbon in the middle already has 2 bonds, so it only needs 2 hydrogens. The carbon at the end has 1 bond. To get up to 4, you'll have to fill in the missing 3 hydrogens. And we have the correct Lewis structure drawn over top of the Linebond structure there. In the case of a structure with heteroatoms, remember you do have to show the hydrogen atoms explicitly on non-carbon atoms. So this nitrogen already has its hydrogen shown. Everywhere with a bend in the line, you know there's a carbon atom. And every carbon atom in this neutral structure should have 4 bonds. And that tells you how many hydrogen atoms to fill in on each of the carbons. And that would be the correct Lewis structure for that compound. We move down to this 3-membered ring with an oxygen at the top. Carbons at every change in bond or bend in the lines. Fill in the correct number of H's to give each carbon in a neutral species 4 bonds, and you have the Lewis structure there. In a case of this structure, a compound called benzene, again, anytime you have a bend in the line or a change in bonding, fill that in. Every carbon in this structure already has 3 bonds, a double bond and a single bond. So each one only has 1 hydrogen. And now you've got the correct Lewis structure from the Linebond structure of benzene. Molecules, of course, have a 3-dimensional shape. So you must be able to represent that in a drawing of a molecule on paper. So this problem asks us to draw a representation of CH2ClBr, and it wants us to have bromine oriented towards the viewer, for which we would use a wedge-like line to indicate a close and a far end of a bond, close to the viewer or further away from the viewer. And they want the Cl to be oriented away from the viewer. To do that, you use this hash type line, where this is the side that is far from the viewer and this is the side that is close. So if we're drawing a CH, H, Cl, and Br molecule, and they want the Br to be pointed towards the viewer, you would need to draw a wedge with a large end of the line oriented towards the bromine, and you would draw a hash line with a large end towards the chlorine. Of course, not all atoms in molecules are neutral, so there is the concept of a formal charge. And when you're given a structure or you're figuring out a chemical reaction, it's very important to know where the charges are in these molecules. Remember that the formula to figure out the formal charge is the number of valence electrons in the Lewis symbol for that atom, and then you subtract the number of non-bonding electrons, and you subtract the number of bonds. Sometimes, instead of saying subtract the number of bonds, people say subtract half the number of bonding electrons. An easy way to figure out the formal charge of an atom, say the oxygen in this structure, will be to draw its Lewis symbol, or just look at which column in the periodic table it's in. Oxygen is in column 6. It has 6 valence electrons. So in the formal charge you would have 6 minus however many non-bonding electrons there are, 1, 2, 3, 4, minus how many bonds are going to that oxygen. There's 1 to the hydrogen and 1 to the carbon, so that's 2. 6 minus 4 minus 2 is 0, so you don't have a non-zero formal charge. This question is asking us to fill in all the non-zero formal charges. Likewise, any carbons that have 4 bonds, no non-bonding electrons, and 4 bonds, will also have a formal charge of 0. So a carbon bound to 3 hydrogens and oxygen has a formal charge of 0. Hydrogen, of course, is the first atom in the periodic table. It's in column 1. It has 1 valence electron. If it makes 1 bond and has no non-bonding electrons, no lone pairs, it's going to have a charge of 0 as well. So in the first structure, there are no non-zero formal charges. As soon as you start to move away from structures with the correct number of lone pairs and bonds, like the oxygen in this structure, you'll start to encounter some non-zero formal charges. So if I have an oxygen and it has 6 valence electrons, and now it has 2, 4, 6 electrons around it that are not making bonds, and it has 1 bond, I subtract those non-bonding electrons, I subtract the bond, I get a minus 1. So the charge on that oxygen is negative 1. All the hydrogens in the structure are making 1 bond, all the carbons in the structure are making 4 bonds with no lone pairs. Those formal charges would be 0. So that's what happens if I take an oxygen, instead of have 2 bonds, I have only 1 bond to it. What if I now add a 3rd bond to the oxygen? It's too many bonds instead. Well, oxygen should have 6 electrons in its valence shell. I have to subtract these 2 non-bonding electrons, and I have 3 bonds, 1, 2, 3. Now I have a plus 1 as the formal charge on that oxygen. And again, the hydrogens have 1 bond in the structure, the carbon has 4 bonds. Those have a 0 formal charge. So let's go over to the right column and look at the structures given here. Now this is a Linebond structure, so remember that you do have some hydrogens on these carbon atoms that aren't shown. So let's fill those in first. So each of those carbon atoms has 4 bonds, no lone pairs. Those carbons will be neutral, no formal charge that is non-zero. And for bromine, if we look at the periodic table and draw its Lewis symbol, we have 7 valence electrons around bromine. It means it should make 1 bond and have 3 lone pairs. All right, so it has 7 valence electrons. Let's check the formal charge of the bromine in this particular structure. We have 7 valence electrons minus however many are non-bonding. In this case, that's 4. And we have 2 bonds. Take away the 2 bonds as well. 7 minus 4 minus 2 is 1. Positive 1. So the formal charge on that bromine is plus 1. Now if we go down to these structures for carbon with only 3 bonds around it, we can figure out the formal charge of the carbons. Now these carbons in the end, on the outside of this molecule, each of these carbons has 4 bonds. So you don't have any formal charge of anything but 0 in those carbons. Those are all neutral atoms. Carbon in the middle here, that's kind of a concern for us for figuring out the non-zero formal charge though. Because a carbon has 4 valence electrons, it usually makes 4 bonds. You don't have any lone pairs, so there are no non-bonding electrons to take away from that. And you have 3 bonds, so it's using 3 electrons for bonds. You're left with a plus 1. So there's a plus 1 charge on that carbon in the middle. Now we can do the same analysis for this compound down at the bottom on the right. You have 4 valence electrons on carbon in a neutral atom. You have 2 negative electrons on the carbon that are not bonding. And you have 1, 2, 3 that are used in bonding. That's a negative 1. So now you have an anionic carbon with a lone pair in the center of that atom. While there are formal charges of positive or negative on some atoms and some structures, it's also important to be able to know, on the basis of electronegativity, where the partial charges are in structures. Where are the polar bonds? Where might electrons be attracted to, or where might you be able to pull electrons from in a particular structure? If we look at the periodic table, the elements that have significantly greater electronegativity than carbon are fluorine, chlorine, oxygen, and nitrogen. And you can have induced dipoles if you have a bromine or iodine as well. If we look at these structures, all the carbon-carbon bonds will be nonpolar bonds. You won't have any partial charges there. We're really looking for heteroatoms, atoms that are not carbon or hydrogen. So whenever we see those, chlorine or oxygen in a structure, or if we had nitrogen or some other atom listed down here, we would have to watch out for those and fill in some partial charges attendant to those structures. If we do that, the more electronegative end of the bond will have a partial negative on it, and the atoms which it's attached will have a partial positive. In the case of the oxygen in this second structure, it's attached to 2 atoms, a hydrogen and a carbon, so both of those will have a partial positive on them. A structure that's just a hydrocarbon, meaning a compound made of just carbon and hydrogen, that won't have any partial charge. None of those bonds are polar. And then we go over to this compound on the bottom left. Electronegative oxygen pulls some electrons towards it. It's a little more negative than the atoms to which it's attached, the carbons. So you have partial positive charge on those 2 carbons. It doesn't matter whether the oxygen is attached with a double or single bond when you're just assigning polarity to that bond. You still have a negative, partial negative on that electronegative oxygen, and a partial positive on the carbon to which it is attached. Some compounds will have several polar bonds, and the entire molecule as a whole will have a dipole moment. The dipole moment is the sum of the vectors of polarity for the different polar bonds in the molecule. So what we do first is fill in vectors to represent the direction in which electrons are pulled for each of the bonds in each of these molecules. So it's just like the previous question. We say, okay, we have partial positive on all the carbons here, a partial negative on the oxygens. We'll fill those vectors in. Down here we don't have any polar bonds. Down here we have 1 polar bond for the chlorine. Here we have 2. So we have all the vectors filled in representing the polarity of each bond in each molecule. Now we have to draw vectors that I'll represent in red, showing the sum of those vectors. Well, if I have 1 vector in this CO2 molecule pulling to the left and 1 to the right, those cancel each other out. So we have no dipole in that case. No net dipole for the whole molecule. It's not saying the bonds aren't polar. It's saying the whole molecule itself has polar bonds that cancel one another out insofar as the direction they're pulling. Here we only have 1 polar bond, so the dipole for the whole molecule pulls in the same direction. And then we get to the case here on the far right, which has one dipole moment pulling to the right, one pulling to the left, one pulling up and to the right, one pulling down. These all cancel out. They're all just tugging in different directions on the central carbon atom. So again, you have no dipole here. And this question is asking you which example molecule in each row has the greatest dipole. That would be this one for the first row. In the second row, this has no dipole because there aren't any polar bonds. And then this one has a dipole going in that direction. There's only one polar bond. Here you have two polar bonds. And if you add those up, if you know how to add vectors, if you start at the same point and you draw the two vectors like this, you have a sum of those going out in that direction. So the net dipole for that molecule is now shown in red right here. And two polar chlorine bonds, and not canceling each other out like all four of these, but pulling towards the left and up as drawn here, those will have a greater dipole for the whole molecule than only one carbon-chlorine bond, like the one in the middle has. Now the types of intermolecular forces between molecules in a sample can have a significant effect on the properties of a container holding a sample of that particular compound. And the ones we're studying in organic chemistry at this time are indicated up here: London dispersion forces, dipole-dipole interactions, or hydrogen bonding. If you don't have any polar bonds, you will have London dispersion forces or van der Waals interactions. If you have polar bonds, you can have dipole-dipole interactions. And if you have a specific type of polar bond, an H attached to an oxygen or a nitrogen or a fluorine, compounds that have those units are capable of what are called hydrogen bonding, because you have a very positive exposed charge on a hydrogen atom in those cases. So polar bonds with a hydrogen in that pole lead to molecules that can engage in hydrogen bonding. So let's go ahead and fill in these different forces. London dispersion, because there are no polar bonds. You can have an induced dipole when you have a halogen like bromine. You could have dipole-dipole interactions then. And then the OH unit is a polar bond with a hydrogen. You can have hydrogen bonding there. At the bottom we have a bunch of molecules, 3 molecules, and they're just made out of carbons and hydrogens, and you can't have any other polar bonds or hydrogen bonding in those cases. All right, so we filled in all of these types of intermolecular forces. Our next task in each row of compounds would be to select the one with the highest boiling point. The highest boiling point is for the molecule that has the greatest strength of intermolecular forces holding them together into liquid state. So hydrogen bonding is going to win out over dipole-dipole interactions or London dispersion forces in that case, as well as in that case. But what happens when we have molecules that only have the same force as one another? I can't say that one of these types of forces is stronger than another. What I can say is that if I have a long molecule, I have more of those forces. I have those forces extended over a 1, 2, 3, 4, 5, 6, 7, 8, a 9 carbon chain. Over here I have only a 4 carbon chain length of London dispersion forces. So I can say that the highest boiling point will come for the molecule that has the longest stretch over which those forces are acting.